after 0.5 microseconds. So I'll just put 0.5 microseconds and you can realize, okay, it's gone after, right? So I could, right, I didn't have to give myself. So the question that we're going to ask ourselves is, do they make it to the front of the rocket? Now, but I'm going to wind us up there by asking three kind of tough questions, all right? And some of them are easier than others. How long do I think it takes the beam to get to the front of the rocket ship? How long does my twin sister think it takes the beam to get from the back to the front of the rocket ship? How long does the beam think it takes to get from the back to the front of the rocket ship? And do they make it? That's the questions. So guys, that's a lot of questions. Let's do them one by one. I'm going to do, in some senses, this is the most difficult one. I'm going to start here. How long do I think it takes for them to get from the back to the front? Now, I've got to do a little bit of setup before you actually try doing any calculations. How fast is my twin sister moving? 0.8 c, right? Because she's in the rocket. The rocket's moving at 0.8 c, she's moving at 0.8 c. Is she ever going to get to the front of the rocket by standing there? So, the thing that we have to understand is that in order for anybody to get to the front of the rocket, from my point of view, they've got to be going faster than 0.8 c or they're never going to get there. So if, I'm just going to make a number up, if I figure out that the beam in my reference frame is moving at 0.9 c, right, if I calculate that, what is the rate that it approaches the front of the rocket ship? Exactly. Does everybody see that? If I calculate that it has a speed of 0.9 c, 0.8 of that is just keeping up with the rocket. 0.1 advances it to the front. So it's a relativity problem. All right? So it's the relative rate of the beam compared to the rocket from my reference frame. In my reference frame, the rocket goes 0.8 c. In my reference frame, the beam goes 0.9 c. So it gets towards the front of the rocket at a rate of 0.1 c. Important idea. That I can't use 0.9 c to get to the front of the rocket because that's not what we've measured. We've measured how fast it's going relative to me, which means that relative to the rocket that I'm looking at, it's going at 0.1 c to the front. Everybody got that? So here's the thing. In order to find that time, the good news is high school kicks in yet again. The relativity stuff, as soon as we take care of it, distance equals rate times time. I don't need anything more complicated than that. All right? So it's just distance equals rate times time. But I do need to know the distance. So step one, how long is that rocket for me? Step two, how fast do I think the beam is going? Step three, how long does it take a beam that's going that fast to get to the front? That's just one of the three questions. Did I mention there will be a question like this on the final? Brandon, that was exactly the right answer. He goes, no, I don't know, I didn't probably roll my eyes quite enough. No, look, this is why we're doing this today. It's going to be easy by the time we're done. It really isn't bad. The whole trick is take it a step at a time. So, let's start. Length. You can almost do this because if you just look at the problems you've already solved, it's now 100 meters instead of 1,000 meters. So based on the answer you had before, if it's going 0.8 c, how long do I think the rocket is? Just look at your answers. It should be the same exact gamma we already solved. Here's the first one we did. So it should be 80 meters or 60 meters. One of those two, right? We did both. If I use this for the velocity, remember it goes the other way. So we're going to end up, it's the Rick number, but you know how to calculate it. So maybe you need to practice it. Does everybody understand that the observed length is 60 meters? Are we good with that? So we're going to say, what do I write? This or this? For 60. This equals 60 meters. This equals 100 meters. Okay? John, in case you don't know, you've taught this, right? Does not use a script alpha properly.
Okay. Yeah, I'm not sure this book. Yeah.
Okay, but yeah, Harvard does. All right. So I've got this. What's the next step I take? So guys, what's the next thing I know? If I know how long the ship goes, what's the next thing I need to know? How fast is this moving? What's the letter I'm looking for? So, because we did this before, if you need to do it more graphically, what's this frame that I'm standing in? S. What's this frame? S prime. All right. So now the question is, what is this? in terms of letters that we've talked about? U prime, because it's the speed in the prime frame. So I know U prime equals 0.6 c, all right? Then what do I need to know? I know that V is equal to 0.8 c, and I want to know what is U for me, all right? So I have U prime, I want to find U. And so we kind of have done that, but let's do it again to be sure we get actual real numbers now. You gave it to me as 0.95, or was it? All right, so actually we've done this. It should be in your notes. This is 0.95c. I think if we, this is rounded, but it's good enough. So here's my question. Now what? I found out how fast the beam looks like it's moving to me. I want to find how long it takes to get to the front, and I've sworn that distance equals rate times time, so the time should just be the distance over the rate, and the distance is 60 meters, but what's the rate?
0.15.
What's that?
0.15.
Good. 0.15, not 0.95, but 0.15. Does everybody see that? Right? Because if I see the rocket moving at 0.8c and I see my twin sister moving at 0.8c, she never gets to the front of the rocket, does she? So it has to be the answer has to be any part of that that's faster than the rocket. So if the rocket's going 0.95c, the beam is going relative to the rocket 0.15c. And c, of course, is 3 times 10 to the 8. And somebody with a calculator who's willing to punch some numbers for me, tell me the time. 400. Oh, c. You have to divide by c. 3 times 10 to the 8. No, this is what's cool. 1.33 what? All right. So basically, what that is 1.33 microseconds. And I tell you that these things go poof after half a microsecond. Do they make it? Lovely silence. I have a question for you. Does my tritium beam know that my sister or I exist? Nah, pretty stupid beam. No brains at all. The only thing it knows is it exists. All right? So whose reference frame is it most important? Mine or the tritium beams as to whether or not it makes it? It's a tritium, right? But we're not going to go there yet. We know that's the right answer, but we're not going to go there yet because the next thing I want to say is, okay, we found out how long I think it takes. Now, I want to know this. How long does my sister think it takes? So, in her reference frame, what is the length of the rocket?
100.
Exactly. Why?
Who's that wife? Because she's inside. And it's
Because
not
she's inside, and therefore, it's what kind of length is it?
a proper.
Exactly. She's at rest with respect to it, so the length she measured is a proper length, so she gets the full 100 meters of the rocket. How fast to her is the beam going? All right, so she has the 0.6c. Do I need to do any doctoring? Do I need to plug in any other equations? No, she's got a speed for the beam, she's got a length that's got to travel, and so t is equal to 100 divided by 0.6c, which equals what? That's meters. Don't forget c is 3 times 10 to the 8. Brandon, are you working on these or are you just grumbling? Yeah. You can't get any scowls if you don't actually work on these. I know it's hard because the table's behind you and I'm in this end. So just turn the table around. Yeah, Danielle? All right, so what she said is 5.5 times 10 to the negative 7, and so what I'm going to do is say 0.55 times 10 to the negative 6, or 0.55 microseconds. Do they make it? No, close but no cigar, because these things have a really finely tuned clock, and at 0.5, except for, do I care what my sister thinks? She cares what I think. And so maybe we're not done yet. Maybe the people we need to be concerned about are these tritium people, if those be people. All right, so here's the tricky part. How long do the tritium particles think the ship is? Now here's where it gets tricky. From the reference frame of the beam itself, do those particles think they're moving? No, they think they're parked, and they think the ship is doing what? Moving that way. How fast?
0.6.
Exactly, 0.6 c, because the speed the ship thinks the beam is moving is the opposite as the speed the beam thinks the ship is moving. So it's 0.6 but negative 0.6 c if I'm going to be really picky about it, right? Not that it's going to matter a whole lot here, all right? So if I've got the ship moving at 0.6 c, and it's 100 meters per second. Now again, we calculated gamma for this. Do you remember? We calculated gamma for 0.6 c. What did we get? It was 10/8, right? And so what does that tell me the length of the ship's going to be? If I take 100 meters and divide by 10/8, all right, so we get the length is 80 meters. Again, you can double check your notes. We did that. Cool. So I've got the length. How fast does the beam think the ship is moving? At negative 0.6, right? So again, the negative doesn't really matter in terms of the time, but it matters in terms of the direction. But we're good with that. So I'm just going to go ahead and say the 0.6 c. And I'm kind of looking at the absolute value because I'm just worried about the time as well. So how do we get the time? Well, the time should be the distance that the beam sees that the ship needs to travel divided by the time of travel. I mean the speed. And what do you get?
Point four.
For a while, right? 0.44.
Yes.
And again, it's going to be 0.44 microseconds. Okay. Do they make it?
Yes.
And now the question is, do they really make it? That sounded not quite as sure. So, do they really make it? It's the $10,000 question. Do they really make it?
Depends on the reference frame.
That's not a bad answer, except for at the end of the day, they either really do or they don't. All right?
They do.
Does it make sense to you that if they make it in any reference frame, they make it in all reference frames? In the sense that, I worded that wrong. If they make it in the right reference frame, then they make it in every reference frame. If they really make it, no matter where you are, then they make it. Because we can put a detector there and say, yeah, I got hit by a beam. And it can't read different just because you're moving. So the question is, out of the three cases we did, me on the ground, my twin sister, or the beam itself, who is right about making it?
The beam.
The beam, because they're the ones that have clocks say, hey, I may live for 0.5 microseconds, and when my clock says that's up, I'm gone. But the beam said, hey, it only takes me 0.44 microseconds. I made it. Well, where did these other numbers come from? Which of these numbers, if any, because I told you there isn't always one, but which of these numbers would be proper times? Why? Remember, I told you, if one of them is proper time, then the smallest one is the it. But we're not guaranteed a proper time. Because as far as the beam is concerned, I'm created, I die, and I'm in the same place the whole time. The ship has moved past me, but I'm staying right here. So the two events occur at the same place. Therefore, that's a proper time. If that's a proper time, can I transform it to get this? Delta t should equal gamma delta tau, where this is delta tau and this is delta t. What's gamma between these two systems? Let's come here. I'm in the rocket. This is my sister in the beam. So what is gamma for me and the beam? This is the 0.6 one, so it should take you to gamma equals 10/8. Right? Gamma should equal 10/8. So my question is, what does 10/8 times 0.44 microseconds give you?
1.55.
Bingo! You get this answer. Isn't it nice to know that those equations all go in circles like that? That in other words, this hangs together. This is one of the basic ideas of physics is lots of questions have lots of ways to get to the answers, but they better be the same. All right? They better be the same at the end. Now, guess what? We can't just use gamma to solve for the time that we have here. It's because this actually, there's a relative motion going on in this reference frame that we don't quite account for. So you can't just flip over and do this one. But the question I guess that's really important to realize here is those times are widely, widely different. I got almost, well, at least 3 times longer in this reference frame than I got in this one. Now you say, but is that real or did it just kind of look like it happened? Well, do you understand that this is how long I measure that it takes to get to the front? And yet I see them get to the front. And if I know this fact, shouldn't I be puzzled by that? I know they can only last for half a microsecond. And yet I say it takes 1 1/3 microseconds. And it should never have made it, but it does. So what do I just learn? The fact, if it really does make it, that difference in the clock is real. It doesn't just look like it's shorter. It is a real time difference. Otherwise, you know, it wouldn't make any sense that they could make it given those time. But they think that this is how long it takes to make the journey. That's more than enough time. They make it. And that means that they really do measure a much shorter time for the same 2 events that I see. Which is that she fires the gun and the beam arrives. Are we good? Okay. So we're going to look at a couple others here. By the way, guys, I like this question for a lot of reasons. Like I said, this is kind of like a big heads up. I can doctor it in many wicked ways. But I like this question because you really have to get hold of the ideas of the proper lengths and proper times and conversions and the Lorentz transformation equations. All right, so actually, before I move on, because I know I'm just sort of saying open wide, let me pour. Do you have any questions about any parts of that so far? I'm going to be honest with you. I ask that question a lot. Do you have any questions? And it's really rare that I get any. So would you explain to me why it becomes very clear on exams that you did have questions? Danielle?
It makes sense when you explain
You
it.
need to say a little louder.
It makes sense when you explain it, but then later.
In other words, it's because during the exam I'm not sitting there going jabber, 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 jibber.
No, not like that, but I mean like when I have to go back and actually like, do the homework or something like that.
No, this is a phenomenon that I know well, which is why I said I really wanted you here cranking through them today on your own so that you get used to actually doing it. Because watching me do it is a different game.
Yeah, we have questions when we try to do it ourselves.
Yeah. But that's what you were doing right now, is yourselves, right?
While you were talking.
Well, talking, yeah, okay. There's always that problem. All right, so I'm going to look at one in the textbook now. I'm on page 919 for those who want reference, and I'm looking at problem number 52. So page 919, looking at number 52. So if you've got them or not, I'm going to read this to you. A spaceship traveling at 0.9 c goes to a star that is 9 light years away. By the way, what is a light year? John's an astronomer, actually Celestia's an astronomer, he can tell you the answer to this if you don't know. But if I say a light year, what do I mean by that?
Amount of time it takes to travel at the speed of light.
Is light year time?
What's distances?
So you're on the right track, but it's not the time, it's the distance light can travel in 1 year. All right? So light year, by the way, in popular music, light year crops up all the time as a time instead of a distance. So there was one song about 5 years ago where something about loving somebody for light years. And I'm going, that's a long distance to whatever. I don't even know what that means. I'll love you for miles. What? All right, so, but what you want to do is realize that when we have a light year, when we're trying to make units work, it's a year times c. A light year in units is light year. So it's time times the speed. So a light year has units of years times c. Another conversion factor, which I would give you if you ever needed, but it's useful, is that 1 year is equal to 3.15 times 10 to the 7 seconds. Okay, so easily going from years to seconds, which are the more standard things that we have. All right, so we have this star that is 9 light years away. We have a ship that's moving at 0.9 c. All right, before I can even go any further, when I say a ship is moving at 0.9 c, there's a big assumption made. What is it? Vacuum. Do I have a velocity?
Yes.
Compared to what? To the sun. Do I have a velocity compared to the floor? No. So when they say a ship is moving at 0.9 c, there's a tacit assumption built into that the moment they say that. And what is it? Compared, I mean, the thing is, it's not very carefully written, to be really honest. But they want you to make the most natural assumption, which is often wrong in life, but let's do it because we have no other choice. When they say it's going 0.9 c, what do you think they're probably comparing it to? Earth. All right, so if I'm going to have this rocket launch and go at 0.9 c, I'm probably comparing it to Earth. That being the case, this becomes S and this becomes S prime. Guys, so the truth of the matter is, already 5 words into that question, there's a big assumption made that we can't solve unless we figure it out. So what we're claiming then is, if I've got this picture going on, what letter out of all these letters has been given to me? The. 0.9 c is the. All right? And then this is the distance. So we'll just call it x for right now. Have you got that? Does everybody understand how that, I mean, that's actually where people can get tripped up right away, is when I say 0.9 c, what am I meaning? All right, so it's traveling to the star, it's 0.9 light years distant. And now, first question. According to a scientist on the Earth, how long does the trip take? So, when we say that the star is a distance of 9 light years, in what reference frame was that taken? Again, it's not stated, and if I were going to put this on the test, I would state it because it makes me nervous that it's not stated. But I would say, relative to Earth, the star is this far away. Relative to the Earth, the rocket's going this speed. All right? And that being the case then, what we're saying is these are numbers that are measured in the Earth reference frame. Now, there's another big assumption that we make right here, but it's one that we kind of have to make. Is this a proper length? That's a nod instead of a yes. Okay. So why are you saying yes? Or why are you saying nod? Timid nod.
I'm guessing that the scientists measured it on Earth, so it has to be a proper length, right?
All right, so in other words, if I'm on Earth, is the distance from the Earth to the star basically measured in a system at which I'm at rest with respect to that distance? You know what? If you can't answer this, that's healthy, because it doesn't have a really good answer. Is the Earth moving? Is the star moving? Yeah, so being at rest isn't really quite true for this, and yet the Earth's motion, and we have to make a bunch of assumptions, the Earth's motion is so minuscule compared to what else is going on that we're going to assume this is a proper length. In fact, if we don't assume it's a proper length, we don't have enough information to continue. But I agree with you if it makes you nervous that it's not really clear that it's a proper length, but we're going to say the star is always there and the Earth is always here, so that's kind of a proper length. but it's a bit of a cop-out. They should have said, let's assume that this is a proper length for this system. Okay, but having said that, we'll take a look. So if I claim that's a proper length, then instead of writing X, what am I going to write? Little cursive L. Okay? Now, a scientist on the Earth wants to figure out how long it takes the ship to get to that star. Do I need relativity to proceed?
No.
No, because I know the distance and I know how fast the ship is moving across that distance, and so I'm not trying to compare velocities or anything else like that. So I can find out how long it takes in my reference frame. It's as easy as d equals RT, right? I just have to say, with that information then, the time is going to be the distance,